We're going to finish up the videos today talking about the mole. And I want to make sure that you spend the most of your time thinking about this concept. And I'm going to send supplemental videos as well, because there are various ways to explain the mole, and it may help you. Somebody else's way of explaining it may be more clear to you than the way I would explain it. And so if you look at 2 or 3 different ways in which this is sketched out, it might be helpful. The mole is a way of representing a number of or amount of a compound. For example, eggs are sold as a dozen. Paper is sold as a ream. A ream of paper, by the way, is 500 sheets of paper. Obviously, you know that a dozen eggs is 12 eggs. Some people sell things in what's called a gross. A gross is 12 times 12 or 144 of something, and so forth. The mole is just another term that's used specifically in chemistry to represent a specific amount of a compound. So, how much does a mole contain? Well, a mole is linked to the actual molecules involved by a constant known as Avogadro's number, or Avogadro's constant. And Avogadro's number is the number of molecules in a substance. And that is what is a mole. And it is represented by the number 6.023 times 10 to the 23rd molecules. So just like 12 is a dozen eggs, 144 is a gross of pencils, and 500 sheets is a ream of paper, a mole of any substance, any compound, it represents 6.02 times 10 to the 23rd molecules. That's a number you need to remember. 6.02 times 10 to the 23rd molecules. Also, the link of a mole to something that we can actually measure, so you can't sit there and count molecules until you get 6.02 times 10 to the 23rd, but what you can do is weigh the mass of a substance. And as it turns out, a mole also, in addition to equaling 6.02 times 10 to the 23rd molecules, it also equals the amount of a substance equal to its formula mass represented in grams. This is also called the molar mass. So when we calculated, for example, sodium chloride, if you recall, we calculated that formula mass as about 58 AMU, or atomic mass units. If you represent that in grams, so 58 grams, that's the molar mass for sodium chloride, and that has 6.02 times 10 to the 23rd molecules of sodium in it. So each sample contains, of the above pictured samples here, contains 6.02 times 10 to the 23rd, or 1 mole of atoms. And if you look in the periodic table, each of these is also the atomic mass of the element. So zinc's atomic mass is 65.4 AMU. If you weigh out 65.4 grams of zinc, you have 1 mole of zinc, and you have 6.022 or 6.023 times 10 to the 23rd atoms of zinc. And that's true for each of these things that is represented in this picture. And you can see that some are big piles of stuff, others are smaller piles of stuff, some is powder, some is wire. But in every case, there's the same number of atoms represented. So each of these samples here also represent 1 mole of the sample. So if you start with the top, you have octanol in a glass, in that little glass there, and its formula is given. If you want to calculate the formula mass, you'll find it's 130.2. In that little vial is 130.2 grams of octanol, so it has exactly 1 mole of octanol and exactly 6.02 times 10 to the 23rd molecules of octanol. Rotating around to the red powder, that's mercury chloride or iodide. 454.9 grams of mercury iodide is 1 mole of mercury iodide. Again, if you look in the periodic table and calculate out the formula mass for mercury iodide, you'll see it's 459.9 AMU. The other vial toward the front here is methanol, or CH3OH. Its formula mass is 32 AMU. Its molar mass is 32.0 grams, and that vial contains exactly 6.02 times 10 to the 23rd molecules. And then in the front here is elemental sulfur, S8, which has a molar mass of 256.5, and that tray there has exactly 6.02 times 10 to the 23rd molecules. So let's see how we would go about converting from one unit of a substance to another unit of a substance. So here's an example. The daily requirement for potassium is 4.7 grams. How would you express that in moles of potassium? Well, the way you would do that is the following. You start with the mass of the potassium. You would divide that by the molar mass, and it would give you the number of moles. So you would take the molar mass, which from the periodic table is 39.10. You'd express that as grams per mole, not AMU. And then you would take the 4.7 grams, divide that by 39.10, and you would end up with 0.12, two significant figures, moles of potassium. You'll also notice, if you do the dimensional analysis of this, that the grams cancel out, and you're left with the number of moles. A liter of air contains 0.00092, or 9.2 times 10 to the minus 4th moles of argon. What is the mass of the argon in a liter of air? Well, here's how you would do that. If you have moles, then you multiply by the molar mass. In the previous example, we divided by the molar mass because we had the number of grams. In this one, we multiply by the molar mass, and it gives you the mass of the argon atoms that is in the air. So the molar mass of argon is the atomic mass expressed as grams. Looking on the periodic table, it's 39.95 AMU, so now it's 39.95 grams per mole. Then you take the moles of argon multiplied by the molar mass, and it gives you an answer of 0.037 grams of argon. Again, if you do a dimensional analysis, you'll find that the moles cancel out and you're left with grams. How many copper atoms are there in 5 grams of copper? Now remember, a mole has 6.02 times 10 to the 23rd grams of atoms of copper. So you have to convert this grams to moles first. Then you take the number of moles and multiply it by the constant 6.02 times 10 to the 23rd, and it tells you how many atoms you have. So you start with the mass, you convert that to moles by dividing by the molar mass. Then once you have the number of moles, you multiply by Avogadro's number, and you're left with the number of copper atoms. The molar mass of copper from the periodic table is 63.55 grams per mole. So you take the mass of copper divided by the molar mass of copper times the constant 6.02 times 10 to the 23rd. So you take 5 grams divided by 63.55 grams per mole, that leaves you the number of moles, and multiply that by 6.02 times 10 to the 23rd atoms per mole, and that leaves you with 4.74 times 10 to the 22 atoms. So stop the tape at this point and see if you can calculate how many moles there are in glycerin. Now, unfortunately, I have to show you the diagram here because I forgot to write out the formula for glycerin for you. But there's the formula for glycerin. And see if you can figure out the number of moles of glycerin there are. This diagram also tells you how to do it. You take the mass of the glycerin, 28.35 grams, and you divide that by the molar mass of glycerin. Now you know that you have to calculate the formula mass first, and then you express the formula mass as grams per mole, and that tells you the molar mass. So the mass of glycerin in grams divided by the molar mass of glycerin will give you the number of moles. So here's the box calculating the formula mass and thus the molar mass of glycerin. Glycerin has 2 atoms of carbon, 5 atoms of hydrogen, 2 atoms of oxygen, and 1 of nitrogen. The carbon's 12.01, hydrogen's 1.008, oxygen is 16, nitrogen is 14.007. 1 times 14.007 is 14.007. 2 times 16 is 32. 5 times 1.008 is 5.040. And 2 times 24.01 is 12.01 is 24.02. You add that up and it's 75.07. So the formula mass is 75.07 AMU and the molecular mass is 75.07 grams per mole. So you take the original mass that we had and divide that by 75.07. So 28.35 divided by 75.07 tells you that the mass, the mole, is 0.378. I should actually express that as 4 significant figures. I made a significant figure mistake on this one because your original number was given to you as 4 significant figures. One more example. The daily allowance of vitamin C, which I've given you the formula here, is 0.000142 moles. What is this in grams? Well, in order to do this, you need to first calculate the molar mass of vitamin C. Once you know what the molar mass of vitamin C is, you can multiply that by the moles of vitamin C you have, and this tells you the mass of vitamin C that you have. So the molar mass of vitamin C is given down here as a calculation. I didn't put a table in there, but it's 12, which is carbon 12.01 times 6 plus 1.0008 times 8 times 16 times 6, and you add up that and then divide it or multiply it times the number of moles you have, and you get 0.0250. And this time I did express it by the proper number of significant figures. And here is a diagram just to review with you how you go from moles to mass. You start out with moles, you multiply by the molar mass, and this gives you the mass of vitamin C. Now this is the last problem we'll do. This is a structural formula for saccharin. And saccharin, if you have a packet of saccharin, you have 40 milligrams. how many molecules of saccharin are in this 40 milligrams of saccharin. I'm going to give you the formula in just a second. Here it is. You start out, you have a mass of saccharin. Now notice it's in grams because your molar mass is grams, so you have to change that previous, you have to change that 40 milligrams to grams. And then you divide by the molar mass of saccharin, which gives you the number of moles of saccharin you have. And then lastly, you multiply by Avogadro's number, and this tells you the number of molecules. And here is the calculation that I did. You take carbon, which is 12 times 7, and don't get stuck on the fact that I didn't use 12.01 and 1.008, etc. I just rounded them off to make it easier to put it on the slide here. So you take 12 times 7 plus 1 times 5 plus 14, which is the atomic weight of nitrogen, times 1, 16 times 3, and 32 times 1. 32 is sulfur. You add all that up and you get 103.18, and that's the molar mass of saccharin. So you take the 40 milligrams, which is 0.04 grams of saccharin, and you divide that by 183.18 grams per mole. And this, multiplied by the Avogadro's number, tells you that you have 1.31 times 10 to the 20 molecules of saccharin.